Hey, it's Mrs. Francis here, and in this video I'll be explaining arithmetic and geometric sequences, so let's get started. First, we want to consider mathematical patterns, and in this case we're looking at a sequence, and a sequence is an ordered list of numbers. The three dots on the end mean it's an infinite sequence, it goes on forever. Each number in the sequence is considered a term. The nth element in a sequence usually starts at 1, so the first element is n equals 1, the second element n equals 2, and so on. The value of the nth term is represented by a sub n, so a sub 1 is 2, a sub 2 is 4, and so on. Now, understanding the notation, if we're talking about a sub n as the nth term, then a sub n minus 1 is the term before a sub n. And a sub n plus 1 is the term after a sub n. So in this example, if a sub n is 6, a sub n minus 1 is 4, and a sub n plus 1 is 8. When we're looking at sequences, we have two kinds, arithmetic and geometric. And the first kind we're going to look at is arithmetic. And in arithmetic sequences, we have what's called a common difference. So in other words, the difference between the terms, consecutive terms, is the same. And for our example here, the common difference is 2, so d equals 2. And there's two different kinds of formulas. We have a recursive formula and an explicit formula. The important thing to remember is that with the recursive formula, you have to know the value of the term before and the common difference. In the explicit formula, you just need to know the value of the first term and the common difference. So for this example, if we were going to find the value of the sixth term, we could really use either of these formulas. And we would get, for a sub 6, we would get 12. Now it's important to look at the graph of an arithmetic sequence. I want you to recall that linear functions graph as lines. Equal changes in the input give rise to equal changes in the output. If we were to put our sequence into a table and the input value would be n, starting at 1 and going to 5, and notice the domain of our input value for a sequence is a set of natural numbers, the counting numbers, and the output would be the sequence. And if we were to plot that in a graph, you would see that it is linear. So arithmetic sequences graph as lines, and we have the same as we do in a linear function. Equal changes in the input give rise to equal changes in the output. Now, the other kind of sequence we talked about was geometric sequences. In geometric sequences, the ratio between consecutive terms is constant, and we call that ratio r. So here's an example of a geometric sequence. And we're looking here at the ratio between the terms. So 12 divided by 4. 36 divided by 12. All of these equal 3. So since that's the case, this is considered a geometric sequence, and r is equal to 3. Now, in geometric sequences, we also have recursive formula versus an explicit formula. And the same as in arithmetic sequences, a recursive formula uses the value of the term before. In an explicit formula, we're using the value of the first term. And of course, for both of these, you need to know the common ratio. So if we wanted to find the sixth term, we could use either of these formulas. And in this case, the value of the sixth term is 972. But keep in mind, if you wanted to find, say, the 32nd term, you wouldn't be able to use the recursive formula because we don't know the value of the 31st term. Now let's take a look at the graph of a geometric sequence. I want you to remember that when we look at an exponential function, the graph looks something like this, if we have exponential growth. In a geometric sequence, again, if we use n as our input value, and that would be the domain of natural numbers, the counting numbers, and our output value is our sequence, we go ahead and show that graph. You'll notice that we have an exponential looking graph here. So geometric sequences graph like exponential functions, and they have equal changes in the input because the output causes the output to be successively multiplied by a constant. So that would be our common ratio. So in summary here, arithmetic sequences have a common difference. The common difference is the difference between consecutive terms. Arithmetic sequences are linear functions whose domain is the set of natural numbers. Geometric sequences have a common ratio. The common ratio occurs when the ratio between consecutive terms is constant. Geometric sequences are exponential functions whose domain is the set of natural numbers. A recursive formula defines the terms by relating each term to the one before it, and an explicit formula expresses the nth term in terms of n. Well, I hope this helped. You may need to pause here and there. Good luck, everybody.